This is the D2 Incorporated Hybrid Conductivity Temperature Depth Sensor, CTD for short, for oceanographic measurement for determining salinity of ocean water. Pictured here is a shallow water version in an aluminum housing of the D2 Incorporated CTD for oceanographic measurement. Pictured here is the deeper water version, the stainless steel version of the CTD, which is for measuring depths between 2,000 meters up to 7,000 meters. We do offer a titanium version as well that can go for depths beyond 11,000 meters, and with our accuracy, our CTD is more than capable of measuring the full ocean depths. We offer OEM custom versions of the CTD that can be packaged and put into anything such as an ice profiler. As pictured here is our ice CTD with conductivity and temperature and pressure. We do offer a standard lollipop design conductivity cell which just has conductivity and temperature, and these are ideal for any measurement under 500 meters because they are very cost effective and can deliver enough accuracy within the first 500 meters of the ocean to be quite effective for measurement. This is the specification data sheet for the CTD and for the ultra-low power version of the CTD that we offer. The ultra-low power version has a lower hertz, however it can operate well below 50 milliwatts. The CTD has a conductivity range of 0 to 7 Siemens per meter, an initial accuracy of 0.003 Siemens per meter. This accuracy and its typical stability allow us to offer full ocean depth measurement with our conductivity cell, as this rivals the accuracy of any other closed field conductivity cell in the market. Our CTD line comes with temperature thermistors that have a range of -5 to 35 degrees C, a resolution of 0.002, an initial accuracy of plus or minus 0.001, and a typical stability of 0.002 Celsius per month. This allows us once again to meet the highest performance standards. Our temperature thermistor shows a very high response speed and no spiking in the lab with a high-speed probe, 0.065 seconds. We also offer a wide variety of pressure transducers to go with the CTDs. They are user set to the depth and have a resolution of 0.001%. The sampling speed for the standard CTD can be between 2 and 26 frames per second. The low power version of the sensor operates between 1 or 2 frames per second. We call our new patented design a hybrid CTD cell because it truly is. It is a closed field conductivity cell, which makes it similar to the Seabird cell. However, instead of having a third closed electrode across the middle, it uses a inductive drive, which is similar to inductive cells. Thus, it's a new patented hybrid conductivity cell that delivers the same accuracy that closed field cells can, but also has the ability to be free-flowing and have no need for a pump. This particular CTD is a 6,000 meter stainless steel version. They can be built up to 7,000 meters in stainless steel. The standard CTD, as shown, is 8.8 inches long and 2.35 inches wide. We offer stainless steel, aluminum, titanium housings. The conductivity cell is 4 inches long with an inner diameter of 0.3 inches and allows free flushing with no pump. This is the most unique feature of the sensor. 65 millisecond response temp probe T63. This is the D2 Inc. Hybrid Conductivity Temperature Depth CTD sensor. 2 versions of the technology have been built. One capable of full ocean depth, another that will be fielded in the Arctic on an under ice profiler. Our CTD cell, a US patented technology, is the first new conductivity cell to enter the market in 30 years. This new conductivity sensor technology allows for smaller, lightweight design, improved precision, and free flushing of the sensor, no pump required. Our sensor has full ocean depth precision and a resolution of 0.001 millisiemens per centimeter. This technology has recently been evaluated and evolved under a joint NOPP grant involving laboratory work and piggyback ocean deployments. The initial deep ocean observations under this program documented a small drift in measured conductivity over time. Fougere et al. Oceans 2021 DOI, you can see the document number on the screen, that was diagnosed to be due to degradation of the annular electrodes in the cell. The electrodes were redesigned, and subsequent deep ocean observations suggest the drift problem has been rectified. Since the redesign of the CTD cell, the D2 Inc. hybrid CTD had CTD ocean data results and lab results that showed no signs of drift and extreme precision. Currently, data are being collected with the new cell design by researchers from Bermuda Institute for Ocean Sciences, BIOS, in partnership with scientists at Woods Hole Oceanographic Institution. These data show that the D2 Inc. CTD obtains data comparable to the operational sensors now being fielded by the ocean observing community. The figures above show potential temperature salinity data, full depth span right, expanded abyssal view left. In this next graph, you can see how the D2 Inc. CTD lines up against the Seabird 911 CTD. Data from the BIOS study here shown on the screen across the full ocean depth, and the Seabird CTDs are the other colors. When you zoom way in at the full ocean depth, near the very bottom of the temperature profile, you can see the sensors are measuring right along with each other all the way to the bottom of the ocean. In addition to deep ocean observations, the response characteristics of the D2 hybrid CTD were assessed by lowering sensors at various rates in Huey's response tank facility. The tank is stratified with cooler, fresher water overlying warmer, saltier water. Double diffusive convention maintains a sharp interference between the layers. Hybrid CTDs were lowered through the interface at several speeds to characterize the transient response of the instrument. The next figure on the screen will show vertical profiles of temperature, conductivity, and salinity at profile speeds of 10 black, 25 blue, and 50 red. 25 and 50 centimeters per second curves have been successfully offset by around 2 meters for clarity. From these data, the T-probe is judged to have a response time of around 0.5 seconds, which is quite typical for standard CTD sensors. The conductivity data shows an abrupt jump at the top of the interface with a more rounded drift into the lower layer conductivity. The latter may manifest reduced flow in the fluid boundary layer within the cell and/or a small thermal mass effect. After response correction, the resulting salinity data show a rapid transition through the interface with no spiking. As described, you can see the tank lowering data here with the 3 different speeds represented in black, blue, and red. And that's why it was concluded that the data shows the D2 Inc. obtains data comparable to the operational sensors now being fielded by the ocean observing community. You can see the D2 CTD strapped vertically to a rosette here and connected to a Woods Hole Oceanographic Institute data logger. D2 also offers battery packs and data loggers for these systems if you require them. And because the D2 Inc. CTD is a closed field conductivity cell, it is not affected by what you strap it to. Therefore, it doesn't matter what type of rosette or other application you have in mind, it will not affect the calibration of the CTD. D2 Incorporated's hybrid CTD was also included in multiple scientific research studies, including the Ice Tethered Profiler study, which was a program with international effort with contributions from, example, the European Union program, Damocles, also the Alfred Wagner Institute for Polar and Marine Research, and of course Woods Hole Oceanographic Institute, who used our CTD to do ice profiler studies. Here you can see the Arctic Ocean location for the ITP program. Ours was included in the top 11 studies. These are the various locations and the extremely important climate studies that were being done in the Arctic Ocean. In the ITP study, the D2 Inc. hybrid CTD was used to collect data for the TOPP 11 buoy. The data for this has been published, and the links are included in the description box. You can see from this map the drift track of TOPP 11 in the Arctic Sea from where the D2 Inc. hybrid CTD provided conductivity, temperature, and pressure data. TOPP 11 was deployed in an ice floe in the Beaufort Sea on September 24, 2023, as part of the Beaufort-Guyot Observing System (BGOS) during the JOIS 2023 cruise on the CCGS Louis Saint Laurent. On the same ice floe, an Ice Tethered Profiler, a U.S. Army Cold Region Research and Engineering Laboratory (CRREL), Seasonal Ice Mass Balance Buoy 3, and a Naval Postgraduate School Arctic Ocean Flux Buoy were also installed. The TOP is operating on a standard sampling schedule of 6 two-way profiles from the surface to 200 meters depth each day. From the ITP TOPP 11 data, you can see the upper profile temperature in this graph here, and the lower graph you can see the full profile temperature. In this graph, you can see the upper profile salinity. In the lower graph from this panel, you can see the full profile salinity in PSU. With this graph, you can see the full profile history. The full record is in gray. The last 3 days upwards is in blue. The last 3 days downward is in red. And the last 3 days show the 50-meter bounce. On this graph, you can see the TOPP 11 buoy status, the drift speed, buoy temperature, and buoy battery voltage over time. On the next set of graphs from the ITP program, you can see the average motor current, the average top voltage. You can see the minimum profile pressure D bar and the maximum profile pressure in D bar. And you can see here in the last two graphs the average profile temperature and the average profile salinity gathered from the TOPP 11 ice profiler. For more information, please visit our website or please meet with us in person at the Ocean Sciences meeting this 18th through 23rd February 2024 in New Orleans. We'll be at booth 142. We will also be attending Oceanology International in 2024 from the 12th to 14th of March in London, England, and there we will be hosting booth B400. We hope to see you at one of the two or at both shows. Thanks for watching our video.